Hi, cohort. Well, we covered a lot of material today in quant, so I thought I would post a series of videos in case anyone would like help or some background material to get started on the homework. So I'm going to post a series of videos. The first one is going to be just a little background about correlation and regression, some slides that I use with my class, and so you might find it helpful to have some background. And then I'm going to post one using this background information on how to do one of the homework assignments. And then I'm going to make one using Sheldon's handouts from today, kind of anticipating what I think we need to know or what was important from his lecture notes. Okay, so here we go. That's not what I want to do. Hold on. Okay, yay. All right, so today's topic was correlation and regression. So one question that people had was, what's a response variable and what's an explanatory variable? So here are some definitions. Your x variable is always your independent variable, and your y variable is always your dependent variable. And so here are just some examples. One way I think of it is the explanatory variable is the one that comes first. So for example, if I look down here at this example, oops, that's not what I wanted to do. Hold on. If I look down here at this example on blood alcohol and number of beers consumed, first you drink and then that affects your blood alcohol. So in this case, number of beers consumed would be your independent variable, your x variable, and your y variable would be the blood alcohol level. Why? Because your blood alcohol level depends on how many beers you consume. Same thing on this one here. Grade on a test, amount of study time. First you study, then you get a grade. So since this one comes first, this is the independent variable. Our independent variable x would be the amount of study time, and the dependent variable, or y, would be grade on the test, since your grade on the test hopefully and often depends on how much you study. Excuse me. So this is just a data set that I use with my classes, and this is just data on a bunch of countries in the world, the amount of internet access or usage they have, and their gross domestic product. And so the question we were interested in looking at is there a relationship between the wealth of a country and their internet use? So before we go on, a question you might just ask yourself is, which one of those do you think is the independent variable? In other words, which one of those do you think comes first? Because that's what we're going to make our x variable. Okay, so let's see if you got that right. So here's a graphical display, or in other words, a scatter plot of all that data I showed you in the previous slide. And you can see that they've made the x variable, or the independent variable, the GDP. I hope thankfully that makes sense to you. GDP measures the wealth of a country. So the wealth of a country comes first, and the internet usage of that country possibly depends on the wealth of the country. What does a scatter plot tell us? Well, a scatter plot simply is a way of telling us, should we keep on going? Is this data set worth investigating? When we look at this data set, the scatter plot, we kind of see a trend. It kind of looks like it sort of goes upward to the right. So this might be a data set we want to analyze some more. If the scatter plot was totally scattered, we wouldn't bother with it because we would have no inkling that there's any relationship between our variables. But since it does kind of look like there's a trend, we are going to go ahead and analyze this data set. So this is how you do it on a calculator, and I'll demonstrate this with my calculator when I do the homework problem. But essentially it's as easy as putting your x variables in the first list, putting your y variables in the second list. Here's the calculator commands. Oh, sorry, this is if you want to do a scatter plot. And then you can make a scatter plot on your calculator. So again, what do you look for in a plot? The trend, direction, and strength. Now, if it was perfect, this would be an example of a perfect positive correlation. Why? Because it's a perfect straight line, positive because it's going up, and linear because it looks like a line. Here is a perfect negative one. Why? Perfect because it's on a line, negative because it's going down, and linear because it's a line. Real data never, ever, ever looks like this. Oh, so this was just a thinking question I put in for my classes. You can try it if you'd like. Okay, so how do you measure, since the real world isn't perfect, we need a number that tells us how good the association is between two variables. That number is what we refer to as R. There's a very long, tedious formula to compute R, which we saw demonstrated in class and also is on this slide. In practice, though, we would never, ever, ever do it by hand, and we're always going to use our calculator or some kind of technology. Here are some pictures of some scatter plots and their various R values. So again, here's a perfect one with an R of 1. Here's a perfect negative one with an R of negative 1. Here's a pretty blobby one with an R of 0.4. The closer R is to 0, the worse the association is. 0 means there's absolutely nothing going on. So when we're close to 0, we're thinking, yeah, there's probably nothing going on. Here's a 0. You can tell there's absolutely nothing going on. But here, see how they're kind of clustered along this upward trend? That's a pretty strong association. That's an example of 1 at a 0.8. So here's a slide which tells us a little background about R. Again, it's always between -1 and 1. And we always look to see if it's strong, if it's close to -1 or if it's close to +1. Okay, so one of the really important ideas behind correlation is that correlation does not imply causation, meaning just because you know two variables have a high association, a high correlation, you can never conclude that one causes the other. I'm curious because Sheldon says that it's a statistician that causes or that determines causation. And from a statistician's point of view, I'm going to be real interested in hearing how that happens in our summer class. Oh, okay, so here's another slide just emphasizing it. Sometimes with my students, I just need to kind of emphasize it again and again and again, and they also like to have slides to refer to. So this is just another slide on that important topic. Okay, so now let's go on to regression. So again, I'm going to show you how to find R on your calculator. You find it the same way that you find the regression line. And this is just saying we always like to figure out what we're going to put in for X, what we're going to put in for Y. And here's a formula for the regression line. Whether you use A's or B's or betas or whatever variables you use, as long as you know that the number in front of X is your slope and the other number is your Y-intercept. One of the things that's important is to be able to interpret slope, and I will do an example of this in the homework, so there is an example coming up. So when interpreting slope way back in algebra, like ages ago, the slope means change in y over change in x. So if you've calculated a slope of a regression line and you get a slope of -3, what that means is that, in other words, it would be equal to -3 over 1. For every increase of 1 unit in the x variable, the y variable is going to decrease by 3 units. And like I said, I'll do some examples of this in our next video. So again, some important notes about regression. Only do regression if R is significant. I'm going to do in my next video homework problem number 6 from chapter 8, because that reviews chapter 7 homework and chapter 8 in one problem. When I previewed it, R is not going to come out to be significant, and yet the textbook is going to do linear regression anyway. Ooh, that's really bad practice and never ever done. But I'm going to do it in the next video just because it's a homework problem. But just so you know, in your own work and when you read research, someone should only do regression if R is significant. Why is that a big deal? Because what regression does is it gives an equation that describes a relationship. If your R value tells you there is no relationship, then you shouldn't describe it with some equation because the equation is going to be lousy. It's going to be a terrible predictor. That's why the first step, find R. If R is significant, you know there's an association between your variables. If there's an association, let's describe it with an equation. All right, so that's the first thing. Only do regression if R is significant, unless it's assigned for a homework problem. And then the second thing is only use your regression equation to make predictions within the scope of your data. And again, I'll show that as well. But for example, if your X values only go between 1 and 10, it would be wrong to use that equation to predict what happens if x is 20 because you have no data to show that that trend continued. That trend could be good for a short window of time and then not continue. So when you make predictions, always stay within the scope of your data. Okay, so that's a little background information if you wanted, and in my next video I'll do a couple of examples.